research laboratory as a senior principal research scientist.
Yeah.
Which is, I was also, when I was more same position, but I forgot this kind of exact name. So Jonathan actually was in France in the École Normale Supérieure.
Right.
And then moved to the Japan, University of Tokyo, and got a PhD. And then he actually moved to NTT as a postdoc. And actually, when he was even in the University of Tokyo, we actually had a lot of collaboration through the internship project and so on. So we knew each other in
2004?
Yeah, so
yeah.
between the 18 years. And after Jonathan moved to Mitsubishi, he actually asked me to also join. And it was a great opportunity for me to join. And we actually had a lot of fun collaborations. And especially Jonathan was an expert for the audio processing, like a phase-related speech processing, speech separation, audio separation, and so on. And today, his talk is also about this work, and I'm very looking forward to your recent work.
Thanks, Shinji, for the nice introduction. Very happy to be here, finally visit CMU. Sorry for not coming earlier. And so, I'll be talking today about our journey at MERL towards general and flexible audio source separation. Let's, without further ado, so first, of course, does this work? No, for some reason. Now it works. I'll be presenting today, but this is, most of the work was done by other people than me. So I just wanted to thank collaborators. I've been fortunate enough to have fantastic colleagues and interns over the years. This is, I believe, everybody who contributed to today's topics. So I would like to thank them and acknowledge their great work. Our main goal, I would say, in the past 8 to 10 years at MERL has been to try to build a system that can perform a total deconstruction and analysis of an acoustical scene. And by that we mean, like, if you assume this kind of everyday life situation, you would have a recording of that of the sound that is in that room. You would analyze it and maybe figure out that there are multiple types of sounds, some of them overlapping. You may be interested in separating them. You may be interested in knowing what types of sound there are, so doing sound event detection. You may be interested in transcribing the speech, or even getting a description of what is going on in that scene. So we've done many different aspects of this goal, I would say, but the one I want to focus on today is more the one related to separation and how you can, from such a recording, in a very flexible way, extract a particular sound and potentially use that in order to do better transcription. So this is part of a bigger, or maybe a more famous way to phrase this. Is,
just wait
yes.
a second. The audience in Zoom said that it's a lot of echo.
A lot of echo. That could be because of my microphone. Let me see.
Are you using the mic from the camera?
I believe what is being used is my microphone, my laptop's microphone.
The camera may be better.
Of this camera?
Yes.
I'm not connected to that camera, though. So maybe I should. Should I connect to the camera?
No, I've muted everybody else.
Is there a way to connect to this camera? Is it this thing? Not sure. Does this work? There's also a nasty sound now. Is it this thing? I'm assuming.
Default microphone has changed to microphone next to go.
Okay, that sounds promising. Now,
I don't know that there's really a way for us to test it. So,
Can I see the Zoom meeting real quick?
I'm trying to get to the. So.
I think you sound fine.
But.
I mean, like,
Oh, there you go. Okay.
I think you should just go ahead.
Oops.
Yeah.
Let me try this. And that microphone. Does it? Can people see me and hear me well now?
I think you're fine, and someone online says you sound fine. So I think let's.
Should I?
Now it's fine.
Should I stick to the new?
Yeah, I think the current configuration seems okay.
Okay, so I'll just stay that way, right?
Yeah.
All right.
We'll cross our fingers.
Okay. All right. So where was I? So this this notion of wanting to deconstruct a scene is related to a famous problem in our field called the cocktail party problem, which was devised. I mean, the term was coined by Cherry in the 50s. And the idea was that we humans have this very uncanny ability of focusing on a particular source of interest within a very complex acoustic scene. And the question was, can we reproduce this ability in machines? So if you want to remove some uninteresting part of the scene and focus on a particular speaker, for example, how would you enable a machine to do so? And so we were interested in that problem, and there's been a lot of interest about the cocktail party problem starting, I mean, in the 50s when that problem was stated, but also a lot of work was done in the field of computational auditory scene analysis, or CASA, starting in the 80s, and a very common approach to enabling this the separation of a particular audio source has been to use time frequency mask inference. So this is, I will explain what it is, but this goes as far back as the early 80s with Dick Lyon in a binaural setting, and then the PhD thesis of Mitch Weintraub in a monaural setting. And so the idea is that you have a mixture, a sound recording, a waveform, that you analyze in some time frequency representation. So here's the short time Fourier transform, but back then it would be like a cochleogram or corellogram. And then you realize that because sound sources tend to be sparse in the time frequency domain or in that representation, you can use masks to kind of cancel the parts of the audio that you're not interested in and only keep the ones that you are actually interested in. So if you can build such masks, you can apply them to the representation of a mixture and then reconstruct in some way the masked portions to get back. So you get the masked time frequency representation, and then you can get back to the waveform. So at MERL, we started applying this kind of framework on speech enhancement first. And so we started from a noisy speech, and we wanted to get back to obtain an enhanced version of that speech. And there's many ways you can do this. You can phrase this as a classification problem where you try to classify each time and frequency bin to determine whether they're dominated by speech or noise. And then you can obtain a binary mask that way and reconstruct the speech. Or you can obtain also a ratio mask, so like assuming that the energy of the speech is between nothing, 0, and the energy of the mixture, which is not necessarily the case, but pretty often is, you can try to kind of downgrade the energy of the mixture to that of the speech, and then reconstruct that masked mixture. So this is a typical pipeline. If you assume that you have a mixture Y, which is a sum in the waveform domain of some target signals, for example, speech and some noise, you would get, for example, a short time Fourier transform based time frequency representation. So you get a spectrogram. You use some model, and nowadays this is done using deep networks, to obtain a mask at each time and frequency. You multiply that mask with the original mixture spectrogram, and then you do an inverse short time Fourier transform to get an estimate of your clean speech. At MERL, we started looking at these kind of models, and so originally other groups were also looking at this, and they were using typically as a loss function to train the neural network. They were using mask approximation. They were trying to define an ideal mask based on the true clean speech and the noisy mixture, and then they were trying to to get the mask that is as close as possible to that ideal mask. And there's various ways to define that ideal mask, but I won't dwell on that. But there's a way that works better to do this and that we showed works much better is to do magnitude spectrum approximation, where what you're really interested in is you don't really care what the mask is. What you would like is that once you apply the mask to the spectrum, you get something that is close to the clean speech. And one way to do this is to only focus on the magnitude and forget about the phase for a while. And so you want the mask applied. There's echo. The mask applied to the mixture magnitude to be as close as possible to the clean magnitude. But we realized that actually, if you're going to use the noisy phase or the phase of the mixture to reconstruct, you're in this situation on the top right where the mixture, this is focusing on a single time frequency bin in the complex domain. So these are complex numbers. So you get the speech and the noise that sum up to the mixture. And you're, because you're using the mixture phase, you impose that you constrain yourself to have an estimate that lies along the line that is defined by the mixture. And the best estimate, actually, the thing that is closest to the true speech along that line is this orthogonal projection here, which you can get if you take into account the phase difference between the speech and the mixture. So we propose to have a phase-sensitive spectrum approximation loss function that took that into account, and that greatly improved performance. Then actually, what you really, really want is not even that. It's really the reconstructed speech to be as close as possible to the clean waveform. And so we also propose later on with Zhongqiu, who's now here, to do a waveform approximation where you just basically train through the inverse time Fourier transform. And so this is how you train the model, the loss function you utilize. Then what kind of model were we using? Well, back then we were using typically multiple layers of multiple BLSTM layers. And so we get some sequence of short-time Fourier transform frames as input, a few BLSTM layers, for example. And then at time t and frequency f, you get a mask value. So a single value typically between 0 and 1 that tells you how much you need to decrease your mixture magnitude to get a good estimate of the speech. After working on this, we thought that what was considered back then the holy grail of the cocktail party problem was to separate a speaker among other speakers. So we started focusing on devising a system that could separate multiple unknown speakers, so without any information about the speakers, using a single microphone. So if you use multiple microphones, you can use spatial information. But if you use a single microphone, you're really on your own. You have to rely on the statistics of speech. So the goal was to separate the speakers. And the problem with that we thought there was a problem with the original pipeline is that when you do speech enhancement, you rely on the different statistical properties of the speech versus the noise. But when you want to separate speech from speech, these properties are the same. So how do you do that? So we thought that one way to do this was to not train a neural network to estimate a value between 0 and 1, to say how much speech varies at this bin, because all of the bins are dominated by speech anyway, but instead to output some representation of the sound at each time and each frequency as a d-dimensional embedding vector. And we train the network to output vectors that are such that bins that are dominated by the same speaker or the same source tend to align with each other, and those that are dominated by different sources do not align with each other. And then if you do that, then you can use just a simple clustering such as k-means to separate the bins into two different pools. The nice thing is that this does not care what the sources are. It just cares, but it doesn't care about the nature of the sources. It only cares about whether they are from the same source or not. So the nice thing as well is that you can just use the same kind of system that you were using before, just replacing the output layer to be d-dimensional instead of one-dimensional. And then we propose an objective function to do this, which is we actually propose multiple objective functions. But the first one was this classic deep clustering objective, where basically we have our ground truth as one-hot labels. So this on the y-axis, if you will, is the time frequency bins. All aligned. We align all the time frequency bins, and then we have the sources on the x-axis. So for each source, we just put a 1 or a 0 depending on whether it's dominating that bin or not. And then we actually don't look directly at this. We look at the ideal affinity matrix that you get from that by, if you multiply that matrix by its transpose, for each pair of time frequency bins, you will have a 1 if they're both on the same source, and a 0 if they're from different sources. And this doesn't depend on the order in which you put the sources in the Y. Once you have this ground truth information, you can train a neural network to come up with embedding vectors for each time frequency bin, such that when you use that output to get an estimated affinity matrix, this estimated affinity matrix looks like the ideal one. The problem being that these matrices are actually massive. This time frequency by time frequency could be hundreds of thousands by hundreds of thousands. You do not want to compute them. So a very important trick was to not compute them and instead realize that this Frobenius norm between these two matrices, thanks to a trace trick, can be reformulated as Frobenius norms on much smaller products. So it's no longer like a V transpose, but more like V transpose V. So you can actually have a product in the other direction. So now the big dimension is in the product and disappears. So this was one of the things that made deep clustering possible. This is a quick demo. So we got to do a press release in Japan, and we had the TV come. It was a lot of fun. Here, I'm going to play a quick demo. Changes for the better is Mitsubishi Electric's corporate statement. And I play what my laptop heard and then separated. Changes for the better is Mitsubishi Electric's corporate statement.
鎌倉花火大会が7月19日に開催予定。
Changes for the better is Mitsubishi Electric's corporate statement. All right, and this was run on my laptop back then. Actually, you can, and this has wide applicability. So this is kind of an old demo by now and maybe dated, but it's, there's nothing more 2016 than this particular application. So we applied it just out of the box on this recording where there's actually music in the background and did something okay.
Wrong. National debt of the United States.
You're wrong.
You're wrong. Playing a really
wrong.
That is absolutely
wrong.
Proved over and over again.
Wrong.
We actually had
all right, and let's see what it did.
National debt of the United States. It's playing a really, that is absolutely proved over and over again. We actually had.
You can get the other source if you want. But, so first, we really actually, in that first deep clustering paper, our strawman baseline was to try to train a neural network to output two masks and then compare them with the ground truth and just pick the best permutation, because you don't know which speaker is going to be in which output. And then so we thought, well, maybe we just pick the best and back propagate. But that's never going to work, right? And it didn't work, but apparently we had a bug because later on we actually used that similar kind of permutation-free objective in the follow-up work by Yusuf Izik et al. At Interspeech for when we were doing a second stage enhancement on top of a deep clustering, and that did work. But this is now known as permutation invariant training, or PIT, which is a super famous method, very successful, and Dongyu was able to make it work really well. So too bad for us, I guess we were wrong. It turns out that you can actually train just a network that estimates a mass directly without estimating embeddings. And so, as I said, you just get two estimates, and then you just pick the best permutation when you compare and backpropagate that loss. Turns out that we were able to get much better performance when we combine this with deep clustering. So you could have a network where you have your BLSTM layers, and it has two heads, one that does the embedding and with a deep clustering objective function, and another that kind of gets the mask directly. And that deep clustering objective actually acts as a very good regularizer for the mask inference objective. And in the end, we get better performance with the mask inference head, but it gets really much better by training with the two objectives. Then I won't be talking too much about end-to-end ASR, but we did at MERL a lot of work on end-to-end ASR led by Shinji and Takaaki Hori and Nico Moritz. But so back then, like, there was a lot of excitation about like building a single neural network to do ASR. Shinji was doing multilingual end-to-end ASR, and then we were like, can we do multi-speaker end-to-end ASR with a single deep neural network? So the first thing we tried was to just combine the separation network with the end-to-end ASR. And so you get a speech mixture. You use the kind of architecture I just described to get two estimates. And then you just basically feed both of these estimates, each of them to the ASR system. And you can train them using an ASR loss. And we just pre-trained each of the two networks, then fine-tuned on the ASR loss and showed that we got pretty good performance from that. Anyway, I'll just give them that. But later on, Shinji wanted to go even further and proposed to even do away with the explicit separation and just do purely end-to-end encoder-decoder pipeline for end-to-end ASR. The idea there, so there's no longer an explicit separation. The mixture comes in. There's a mixture encoder. Then it branches out into two speaker differentiating encoder, which are tasked to make their encoding different from each other. And we kind of nudge them in this direction by using a negative Kullback library loss to make them more different from each other. And then they both go through ASR encoder where the weights are shared, and all the other layers are with weights shared. And it turns out that you can train this end-to-end. And on the Wall Street Journal, mixtures of the Wall Street Journal corpus, we actually got similar performance using either explicit or implicit separation back then. So we were getting, 14% character error rate, which corresponded to about 28% word error rate. This is another demo that we got to do in Japan. This time, we wanted to showcase the system, which was both multilingual and multi-speaker. And we thought, well, imagine you're in an airport and you want to go to a particular place of a particular business, and you want to ask the question in your own language without having to tell the system which language you're going to speak. So we built a fake airport guidance system where you could speak in French, in Japanese, in English, I think in German and Chinese as well later on. And it would recognize the speech and then guide you in that language to the correct business. And you could have two speakers also speaking at the same time. So I'm going to show a quick demo. Ramen ga tabetai na. So it guides me to the ramen shop in Japanese. I need to charge my phone. Okay, now in English. And then you can do code switching. Chuka ryori ga tabetai. I would like to go to the bookstore. Je cherche un restaurant français. And it gives the free guidances each in their corresponding language. Finally, the finale is with two speakers.
I'd like to buy a necklace.
All right, so it does the right thing. Okay. Later on, with work led by Shankai, extended this to a multi-channel setting, where we had a fully backpropagable pipeline of kind of interpretable steps with a masking network to guide a beamformer, followed then by feature extractor and then end-to-end ASR pipeline. And later on, Shankai then extended this to use transformer architecture in various parts of the network, in the masking network, the encoder, decoder, and was able to get very impressive performance. So if you remember, I think we had 28% word error rate on a similar data set. I mean, I'm not sure exactly the same mixtures, but very similar data set. With this particular architecture, we were able to obtain 12% word error rate in anechoic conditions. But if you increase the number of channels, then you get even better. If you get reverberant, it gets much worse. But if you now use standard dereverberation, you get back to very good performance. All right. Before we did that work with Franka, actually, there was a tendency that everybody was kind of trying to do speech separation on the same completely clean anechoic data set that we had put out in the deep clustering paper. And our mistake, the data set was like, it was 8 kilohertz, it was completely clean, full overlap. There was a lot of issues with it, and also anechoic. And with the performance was starting to saturate. That being said, back then maybe it was saturating at like 17 or 18 dB, and now it's at 23 plus, so it's still not saturated apparently, but still like extremely clean outputs. And so we thought like we need to go to a more realistic condition, and we proposed to build a new data set that kind of extended the previous one, but had a 16 kilohertz version, included noise that were recorded in real settings. So we worked with a company called, a startup called Whisper AI, and they recorded a bunch of sounds in bars and cafes in the Silicon Valley, in the Bay Area. So we called it the WSJ0 Hipster Ambient Mixtures Dataset, or WAM. And we later on extended it to reverberant conditions as well. And this has been used quite a lot since then. So there's various tasks in that dataset. So the original dataset was just clean, speech separation. You could add noise in WAM, or you could add reverberation or noise and reverberation in WAMR. And we found in the original paper on that dataset, we found that cascaded approaches kind of work pretty well in this. If you first denoised, then separated the speaker, and finally used dereverberation separately on each of the speakers, that's kind of what gave the best performance for us. And the idea being that each of the speakers in a different location, so you should really do different dereverberation steps for each of them. And you can do that step much better if you've already separated them. So back then, we got about 4.7 dB at the output, starting from -6. Still not great, but I mean, 10 dB improvement, but still not a super good number. And later on, with Zhongqiu Wang, we went further. We kind of doubled down on the cascade idea, especially improving on the speech dereverberation. And so dereverberation is a form of blind deconvolution. So it would be great if you knew the source or the filter. You could get the other, but it's kind of a chicken and egg problem. So how can you deal with that? One way to do that is to do supervised learning-based dereverberation. You train a deep network on paired data where you have the non-reverberant speech and the reverberant speech, and you try to train the DNN to estimate the non-reverberant speech, the direct path. But that kind of approach doesn't really explicitly leverage the physical aspect of reverberation, the fact that it results from a physical process, which is the linear convolution between a dry source signal and the room impulse response. There are other methods that exploit that, and so you can, that are played typically based on linear prediction. And so the idea to improve upon this was to combine the DNN and these methods. So originally, a very popular and successful method is called DNN WPE, so weighted prediction error. And we proposed an improvement on this that we called convolutive prediction. Let's assume we have this step that does a better dereverberation. A typical, like a pipeline that you could do would be you get your mixture, you use a first DNN to kind of separate the speech, to get you a first estimate of the speech. Then you use that first estimate to get to do dereverberation, to get a better dereverberated estimate of the speech, and then you could combine that new estimate, dereverberated estimate, the first estimate and the original mixture all together to a second DNN to get yet another better improved speech estimate. And you could iterate, actually. Once you have your better improved estimate, you could maybe do better dereverberation, etc. So I'm just going to spend a couple of minutes just explaining the main difference between the WPE and convolutive prediction. So WPE, the main idea is that you want to estimate the speech from the mixture. So at time t, you only have the mixture. but you want to remove from the mixture at time t the effect of reverberation in the speech signal, which comes from previous steps. So the way WP does this is that it tries to estimate a filter applied to the past steps to remove as much as possible from the current step. The problem with that is that you need a delay, because if you allowed yourself to use time t, you could remove everything from time t in a trivial manner. So you need some delay in order to remove not too much. Another problem, so this is very easily done. First, this is done based on a Gaussian assumption, and it needs, in DNWPE, it needs an estimate of the clean speech magnitude, but it only uses the magnitude, and it only uses it in the denominator as a weight in this least square objective. So several issues. So as I mentioned, it needs a non-zero delay. It only uses the magnitude. It cannot leverage any estimate of a phase of the speech that you may have. And also, because you're removing past samples of the mixture, which includes noise, then you're kind of, what you're removing also includes noise. So if the noise is very prominent, you could actually be estimating the reverberation of the noise almost. So it's not clear that this is not very robust to noise and interferences. On the other hand, what we do is very similar yet different. At time t, we are trying to remove from we assume we have a mixture and a first estimate of the speech. So by the way, everything I'm talking about here is in one frequency, in the time frequency domain. So we're trying to find a filter at a particular frequency at time t to remove that we apply to the estimate of the clean speech, which is what actually reverberation is. It's a filter applied to the clean speech. And then to remove that, it's very annoying that my mouse keeps disappearing, from the mixture. So the equation here is now our estimate of a speech is inside the numerator instead of being in the denominator. We don't need a delay. We use both the phase and the magnitude estimate, so this is a complex value here. And also we can show that we're more robust to noise and interferences. So we train a network to do this task of noisy reverberant speech separation. We also explored different loss functions that are more involved. So junctures models typically estimate both the real and imaginary components in the time frequency complex domain. So you can just have your loss function on these components. But we found out that adding another loss function on the magnitude itself kind of decreases a little bit the performance on SNR type of metrics, but improves greatly on like other metrics such as speech quality, intelligibility, and also ASR performance. So here is the result. So if you remember, we were at 4.7 dB, I believe, in the original Whammer paper, and using this cumulative prediction in between two DNNs, and also iterating, doing two passes of the second part, juncture was able to get to 7.5 dB. All right, so far we've looked at a lot of supervised methods, but we're also interested in how can we train models that do not rely on supervised data. So, arguably, humans probably were not trained by comparing reverberant and non-reverberant paired data, for example, or like speech mixture versus isolated speech. So as a science question, how can we make a system that kind of learns to do that without supervised data? So the first work we did in that direction was instead of assuming that we have paired data, we assume that we have two channels, which in the case of human we do. So let's assume you have two ears, and you're going to use in a very crude spatial source separation algorithm that leverages the spatial information to give you a first pseudo ground truth of a separated speech. And that's not going to always work, because if the sources are very close to each other, your crude spatial separation algorithm is going to fail. So you should not blindly use this blind spatial separation algorithm. We wanted to select samples that are better, that lead to better pseudo ground truth. For example, in situations where the sources are very far apart. So what we propose is like we try to derive a confidence measure for each mixture that you get based on the quality of the clustering of the time frequency bins. For example, if the clustering, on the spatial features, if you ended up with features that all clustered in the same point, it probably meant that you would fail at separating the two sources, for example. And also, we use the confidence of the posterior probability at each time frequency bin of the assignment to a cluster as a way to say whether this crude spatial separation system thinks it's confident about what it output. And by doing so, we were able to kind of select in a smooth way. It was not like either take or ditch. It was really, for each time frequency bin in each mixture, we put a weight on the information that it would then give a deep clustering system to train a deep clustering system to separate single channel mixtures. So we use, at training time we have 2 channels, but at test time we only have 1 channel. And this shows that this confidence measure kind of correlates well with, sort of well, with the SDR of the output of that spatial clustering, of that spatial separation. And it turns out that you can kind of, the confidence helps. These weights that I mentioned help. You get like 1 dB better by using these weights. By using the weights, it's kind of a trade-off between the quantity of data that you have and the quality. So if you really rely on the confidence measure, you're only going to use the very confident point, but of which there's less off. And we found that also in 2 channels, sometimes the original blind separation is better. Sometimes the single channel separation is better. So if you combine both, you can get some improvement. Then more recently, actually, I think this was out last month, we tried another take on the similar setting. And again, we assume that we have 2 channel mixtures at training time. But now we do this, we did things a bit differently. So you assume that you have 2 sources, and you have 2 mixtures at the left and the right channel. And you feed only the left channel to a speech separation model. And the goal of the speech separation model is to separate the sources such that you could predict the right channel from the separated sources. So you could add them together, but that's not going to work because you don't know where the sources are. So there's no way for the speech separation model to output sources that have the correct channel, the correct room impulse response of the right channel, because that depends on where the sources are. Like what you heard at the left channel is going to be different than what you heard at the right channel. They're going to be shifted, they're going to be different scales. So you can't do that. Instead, what we propose to do is to apply a Wiener filter to each source, each output of the network, against the right channel mixture. So at training time, we assume we know the right channel mixture. So we kind of fit each output to the mixture to kind of color it in how it should be in the right channel. We apply that filter, and after applying that filter, we get an estimate. We get a predicted right channel. And our loss function is the difference between that predicted right channel, where we use some oracle knowledge about the right channel, and the actual right channel. And we show that, and this is an oracle experiment where we compare how well you can fit the right channel based on various signals. So if you use as your estimate of the speakers just the left channel mixture, so very bad estimate of the mixture, of the sources, you can, by using Wiener filter to match that to the right channel mixture for both sources separately, then adding that, you only get 7 dB reconstruction. If you use the true reverberant source image signals at the left channel, which is what you hope that maybe your system is going to get, and then apply Wiener filter and reconstruct, you get 12 dB. If you use the dry one, you get 13. So this hints at the fact that this loss function, because it wants to increase the SDR, if the network can give you can separate the sources, it will do better at that loss function. If it can also dereverberate a little bit, it will do even better. So there's hope. Now that being said, this is not, we realized halfway through that the winner filter does not really constrain the network to output independent estimates. It can still play tricks. It can like reconfigure, if a network did not fully separate the sources, it can still reassign correctly the mis-separated portions and get still a quite good reconstruction. So this doesn't work in a fully unsupervised setting. We have to guide it a little bit. So we showed, though, that if you use a semi-supervised setting where you assume you have just a few supervised data, where you have the mixture and the corresponding sources, let's say you have, out of 20,000 mixtures, you have 1,000 where you have the corresponding isolated sources. If you train a supervised model on only the 1,000, you get 3.5 dB SISDR against the true reverberant sources. If you add the 19,000 unsupervised mixtures and you use our loss function, you can get to 5.7 dB. Whereas if you train on all the 20,000, you get 6.6 dB. So we're able to, and this starts at 0. So the supervised model kind of recover on supervised model, only 1,000 sample gets 45% of the way of the top line, and we get 78% of the way. So this is still, I feel like there's still much more that can be done in this work. I'd like to make it fully unsupervised, but yeah, still next time. All right, how am I doing on time? I can't remember what time we started. So so let me maybe move now to more non-speech sounds. And the difficulty in non-speech sounds is that it's even harder to generate realistic mixtures. So the first work we did, we wanted to reduce the amount of supervision you have to give the system in order to train it. So you see that this has been a broad theme at MERL, but in this particular case, we wanted to know if you could train a separation system without using strong labels, which in this case for us means the isolated sources, but like the time frequency, or I mean the actual waveforms or the time frequency representations of the sources, but only using weak information, such as either whether a source is present or not in a clip, 10-second clip, or maybe a slightly less weak, but still weak in our book, from when to when they were active. And turns out you can kind of do that okay. And the thing is, how do you build a loss function that bridges the estimated sources and these labels? And you can use actually a classifier to do that. So you can train a sound event detector or an audio tagger on the mixtures to get these tags, because you have mixtures and you have these labels. And once you have trained your classifier, you just fix it, and you then train the separator such that each of the sources, after they go through the classifier, the separate sources do have the correct labels. I'm going to skip the examples in the interest of time. We wanted to go see if we could do a bit better if we could introduce some amount of information about the frequency, but not the actual signal. So in that case, music is kind of a nice medium, because you can have the score, which gives you both time and some amount of information on the frequency, on the fundamental frequency, but not the whole thing. You don't have the whole spectrum. So we tried to train a music separation system based on score only. And by score here, I actually mean, to make our life easier, we assume we had an alignment, and we actually had the MIDI that generated the audio. And very similar system, instead of using a classifier, we use a transcriptor, which try to transcribe for each time and pitch and each instrument if there's an activity or not. We also considered adversarial loss functions, which I think are kind of cute. In one of them, we try to recover the score, like let's say in the piano output, we try to use the piano output to recover the guitar score. And if you can do that, it's bad. So we try to this kind of decrease. The more you can recover the guitar score from a piano, the worse it is. And we had yet another adversarial fine-tuning where we separated multiple mixtures, music pieces, and then took one output of each, mixed them together so that it looks like a synthetic mixture, and then try to make the transcriptor fail on that mixture. I'm going to skip the experiments. Another direction we explored is that of hierarchical source separation. This stemmed from the fact that source separation problem is kind of inherently ill-posed. Like, what is a source? There may be multiple definitions of a source depending on what you're interested in and the situation. For example, let's say you're listening to people having a conversation, like multiple conversations, while the radio is playing. Do you want to separate? And the radio is playing some band, music by a band. Do you want to separate the band as a whole, or do you want to separate each of the sources? Do you want to separate each conversation or each speaker or just the whole? So, I mean, there's kind of a hierarchical structure of a sound scene, and there's multiple ways you could separate. So the first thing we did in that direction was to build a network that uses the hierarchy of instruments. So if you consider that some instruments are more similar than others, and you want to query a system, you have a song, and you want to say, give me the part of a song that sounds like this, and you play a guitar sound, for example. If you play an electric guitar sound, did you mean that you only wanted electric guitars in that song, or did you want all guitars, or did you want all in kind of harmonically dominated instruments? It's not clear. Like, the intention of the user may not be clear. So we built a system that, like, given a query such as electric guitar, for example, would do all of the above. So it will both have an output that only focuses on electric guitars, another that focuses on the parent, which is all guitars, and then another on that parent, which is guitars and piano, for example. And we showed that by imposing that kind of architecture, we were able to improve separation performance at the fine-grained level with less ground truth data at that level. So we were able to leverage ground truth data at the parent level, so which arguably may be easier to obtain, to improve performance at the finer grain level. A more recent work, actually I don't think it's on arXiv yet, it should be on arXiv Sunday night. So it's in the pipeline right now, which is another way to look at hierarchical separation. And there's been a lot of interest on hyperbolic representations in images and in NLU. And hyperbolic spaces are kind of well suited to embed these kind of hierarchical representations. And so we thought, like, can we do this in audio? Can we use hyperbolic spaces to learn a hierarchical embedding of time frequency bins? And so we tried that on kind of a toy problem. Like, we were just wanting to be very simple. So we built a data set where we had some instruments like bass, guitar, drums, and then male or female speakers, and that our hierarchy in this is going to be bass, guitar, drums, and then music above that, and then male, female, and then speech above that. And so basically what we do is just we project our time, we use a neural network to get us a time frequency embedding, a Euclidean time frequency embedding, like a usual time frequency embedding, that we then project in a hyperbolic space, which is here this called the Poincaré ball. And basically it's, oops, no, I do not want to reply to a call right now. So it's a non-Euclidean space where as the further away from the center you go, the more you can pack. Basically, the distances become, even though they look small, they're actually bigger and bigger as you go near the boundary. So you can pack more and more fine-grained things near the boundary. And also, people have noticed that when you embed in these kind of spaces, if the system tends to embed a particular class, points for a particular class near the boundary if it's more certain about that classification accuracy. And when it's not really sure if it's a guitar or bass, it's maybe going to backtrack a little bit and put the point more towards the center in the music, more like in the more general music kind of embedding. And so it kind of does the job. It performed maybe a little bit better than the Euclidean embedding. But what's interesting about this, if this was more like a study where you can kind of use the distance from the center of a ball as a measure of certainty. And we found that, for example, if you look at the number of active sources at a particular time frequency bin, those bins that have many active sources tend to be closer to the center, and those that are dominated by a single source tend to be closer to the edge. It's kind of intuitive thing. We also showed that the distance to the center is actually very well correlated with a Bayesian notion of certainty that you can get by running the network many, many times using different realizations of dropout. So if you're interested, you have to wait until Sunday night to see this. All right. Now, so I mentioned earlier that we were very motivated by the cocktail party problem, and where the goal is to isolate any source of interest within a complex acoustic scene. And there's been a lot of work on, like, separating musical instruments, separating speech from speech. But surprisingly, until last year, there hadn't been a lot of work on separating movie soundtracks or sound mixtures that involve speech, music, and sound effects. And so that's where we came in, and we thought, well, it's kind of like a tiny, cute version, small version of the cocktail party problem. And so it's kind of like a cocktail fork problem, where you have cocktail forks have 3 prongs. So you separate the soundtrack into music, speech, and sound effects. And I'm going to show. OK, sorry. So this can have multiple applications. You could apply it as a front end for like video understanding tasks. Like if you can separate these streams, argue it's going to be easier to do Q&A or audio captioning. You can use it to improve total transcription, like better speech recognition, better event detection. Or you can use it to have a better source, better listening experience. Like if you're in front of your TV and you want to just listen more to the dialogue without the sound effects blowing at you, you can have this flexible remixing. So we built this interface where you can have a cursor, but you can move more towards the speech, the sound effects, or the music. And I'm going to show a demo. So on the right, you see what we focus on.
Hi, Phil Swift here for Flex Tape, the super strong waterproof tape that can instantly pack. No ordinary tape.
Its triple thick adhesive virtually welds itself to the damage. But Flex Tape grips on tight and bonds instantly.
Plus, Flex Tape's powerful adhesive is so strong, it even works.
All right. It's, so we didn't train on YouTube video. We actually built a data set for this using LibreSpeech, FMA for music, and I think FSE50K for sound effects. We did try to mix it as much as possible as real soundtracks. So we looked at how sound engineers, producers, what levels they use, and we tried to get some variety within that. And so this data set we call Divide and Remaster, or DNR, is actually going to be used in the next sound demixing challenge that was announced yesterday as one of the tracks. There's going to be a music track and then a cinematic sound separation track. So please participate. There's I think the $10,000 worth of prize for the cinematic track. So and Mitsubishi Electric is actually sponsoring. All right. So we can actually, as I mentioned, we can combine this separation with a transcription. So we can, do better transcription at the, so for example, sound detection, activity detection at the output of a separator. But we can also show that classification helps separation. If we get a second separator where we concatenate the activities of each of the 3 sources, music, sound effects, and speech, we can get a slight improvement in separation performance. So this model has information from the activity as well. Vice versa, separation helps classification and recognition. We showed that we can get better performance for music and sound effect detection. And also for ASR, where we showed that you can use the separation to improve performance on LibreSpeech. Actually, we also showed that if you keep a little bit of the other sources, if you remix a little bit the other sources, you can improve slightly performance from 7 dB to 6.2. 7% to 6.2 error rate, because it kind of avoids some artifacts that the pre-trained model doesn't like. I'm going to skip this. I think this is the last topic. Do I have 5 more minutes? Is that OK? OK. So this is the last topic that we work with on with Ephemius, Tinis, where we tried to, again, kind of go at this idea that how you want to slice, I want to cut, like to segment an acoustic scene really depends on the user's intention. And there's multiple ways you can ask for something. So the same target source could be described in multiple ways. For example, if you have like a female speaker speaking in French close to the microphone, you could ask for the female speaker, or you could ask for a French-speaking speaker, or the one close to the microphone. And they're all the same, but these are different ways to ask the question. And so we wanted to build a system that could take any of these queries. So like kind of that's why we call it heterogeneous, because these queries are different in nature from each other. But still, it's the same network that you just feed a different conditioning and can get the same target speaker. Interestingly, we found that by training a system on these different kind of conditions, we were able to get better separation performance than a system that is trained using permutation-independent training, in which then you just select the best speaker, the actual speaker, in an oracle way. So we built a data set for this. I believe it's now on GitHub. We use a conditional version of a sudo RMRF network to do this. And there are some interesting results. So this is very difficult to read. I'm sorry. We spent a lot of time thinking how to present these results. But basically, these numbers show you the percentage of the data that the model is trained on. So when you have 25 everywhere, you have a quarter of the data in with gender-like style query or spatialized query, so close to a microphone or further away. L is the language, so which language it is. And we had 2 different data sets, one of them much more reverberant than the other. And we showed that if you train on these 4 types of condition of data using PIT, you actually do worse than by training, actually asking the network to learn these conditions. And you don't do much further than, these are actually 4 different models in blue. Each time you see 100, that means that we had one model trained on 100% of that data. So each of them is a specialist model trained only on that particular condition. And so we don't go too far from that. And actually, we do better in the language case, because language is so difficult for the network to figure out which language it is that it can't really actually learn that well to separate the speakers in the first place. So you're better off learning to separate the speakers better on another condition at the same time as language, because otherwise, basically, the network doesn't learn anything. Sorry. So we showed that by, so as I mentioned, we had a data set that was a Wall Street Journal that was anechoic, and then another one that was reverberant. And we wanted to do gender-based separation, so condition on gender, in the reverberant domain. But we did not have any gender labels in the reverberant domain. We assume we only have gender information in the anechoic domain. By training, so by using the heterogeneous separation, we add another query, which is the energy, which is a very simple condition. It's like you make one of the speakers louder than the other, and you ask for the louder speaker, for example, which is probably the easiest condition for these kind of networks, and probably what they usually rely on when they actually when you let them do what they want to do. And it's very easy to make these kind of mixtures. You just pick two sources and you normalize them, make them one louder, and you mix them. So you can make this kind of imbalanced mixture very easily in any domain. And we show that by asking the network to either pick the louder or the softer speaker, and sometimes pick the male or female speaker in the anechoic domain where we know who is the male and female. And also asking to separate the network to get the louder or softer speaker in the reverberant domain. It also learns to separate based on gender in the reverberant domain, even though it never saw any gender data in that domain. So it kind of, you're able to do some transfer learning in a way. A follow-up to this work, which was also out last month. So in this heterogeneous condition training, I believe this is my last slide. We have a set of various, when we train a network, we have an input mixture, we have a target source in that mixture, which has a set of conditions, of queries that you can, that matches that particular target. So if it's a female French speaker, you could say female, you could say French. So at training time, we just sample that condition, kind of with the same probability. We found that, and we thought that maybe there was a way that we could improve this, because sometimes the network prefers one of the conditions over another. Even though it's the same target, it does a better job if you ask it for the female speaker than if you ask it for the French speaker, for example, even though it's the same target. So we thought maybe there's a way to to train another network to rephrase the query. So if you ask for a French speaker, it would look at the mixture, try to figure out, actually, instead of asking for French, you should ask for female, because that is going to work better. As a first step along that way, we thought, well, then maybe we should first train a network that tries to do as good as possible, regardless of the, in one of the conditions. Because we want to rephrase the query to the best one, let's first train a system that focusing on doing as well as possible on the easiest query, on the one that does the best. So that's what we did in this optimal condition training. Instead of sampling any condition, for a given target, we look at all the conditions that match the target, look at the performance of the network when it separates based on each of these conditions, and just look at the condition that performs the best, and only backpropagate for that best condition. So the network, in a way, always focuses on the easiest case. You would think that would not work, and I would agree with you, but actually, quite surprisingly, it does better than the normal training. And then we went further, as I mentioned, we introduced another module that takes the mixture and the original condition as input, and then refines the query that it gets passed to the condition network. And we looked at this in a slightly different, similar but different task, where we had we could also use a text description of the target as a query. And we find that surprisingly, actually, this optimal condition training, even though it's trained to perform well only on the easiest query, which is not necessarily the text query, it does improve performance on the text query as well. Sorry. And we also found that this refinement also improved a bit performance. All right. This is actually the last slide. Just looking ahead, what we're just going further towards this total segmentation analysis that we've been shooting for. We've been looking at also integrating localization, separation, and event detection and transcription. Along that direction, one work was this class conditioned sound event detection and localization, which was based on one of the DK's tasks. We're also looking at the audiovisual modeling. We had a paper on using visual scene graphs for audio source separation. We've also started looking at audiovisual speaker diarization. This is a bit misleading because that paper actually does not use it's on an audiovisual speaker diarization data set. We get state-of-the-art performance, but without using the video. So the next step is using the video. And then we're also interested in, as many people are, in using generative modeling, such as diffusion models. And we just had a paper last month on using cold diffusion for speech enhancement. And finally, we are very much interested in self-supervised and unsupervised learning, but that's not out yet, so you have to wait a little bit more. All right, thank you very much. And any questions?
So yeah, I think we have time for a few questions, and then unlike usual, instead of snacks here, we're going to walk on and back to GHC, and we're going to have like a little social there at 6501. So, questions?
I actually didn't fully understand the query condition-based
Yep.
approaches. So query here is not text; it's some kind of a flip or something like that.
In which case? In the original one or in this one?
Yeah.
This one?
That one is.
So this one, you can actually, this one also is heterogeneous. You can still query for which source appeared first or second. Was it more harmonic or more percussive? So this is on general sound. It's no longer on speakers.
Sure.
And or which one, the signal energy, which one was loudest or softest, or the text description. So, which in this case is basically the more like a tag, but we consider it as a sentence. So it's like dog bark, for example. But we pass it to a bird encoder.
Okay.
So all of the above. It can do anything. There's a the bird gives you a conditional embedding that you pass to the network, and similarly, all the other conditions get translated into an embedding vector that gets passed to the conditional separation network.
Okay. Thank you so much.
Yeah.
So you mentioned masking strategies, right?
Yep.
So what are the masking strategies you're actually using in
Right.
several works?
It depends, yeah. So some of them we're actually only implicitly using masking strategies. I think the pseudo RMRF is kind of like that. It's learned. It uses learned time frequency representations. So the masking kind of happens in this space that we don't really understand. That is learned. But in most of the other work, we've been using just short time Fourier transform. And then we apply a mask that can either be a real mask, sometimes that we truncate between 0 and 1. But in other work that I did not present here, we sometimes go further than that because we realize that because of phase cancellations between the speech and the noise, sometimes the magnitude of the mixture is actually smaller than that of the speech. So you actually need to boost the magnitude. But doing that is very risky because this kind of situation typically happens when in a very noisy situation where the phase is wrong. So if you boost the magnitude but don't do anything about the phase, you can get actually further away from the real speech. So the speech may be there, and your mixture is here. And if you keep in that direction and say, well, but I'm going to try to match that magnitude, you end up here, which is even further. So you need to pair that with like improving the phase. So this you need to do some other processing to kind of get a better phase. So it can be a real number, or it can be a complex number, which tries to correct the phase as well and the magnitude at the same time. Or it can also be not a mask. It can be directly, instead of being a mask that you apply to the mixture, you can try to just estimate the speech complex, the complex coefficients of the speech directly. That's the strategy that typically Zhongxiu uses, and that works really well.
Yeah, the other question goes along with the magnitude of spectrum and phase, right?
Yeah.
So we know that by just reconstructing magnitude spectrum, you can still hear without, I mean, if you're not an audio expert,
Yeah.
you cannot tell the difference that much, right? How do you, what's your comment on the phase information's importance? It's getting more and more important
Right.
in the recent years. Like,
Yeah.
but we still estimate it wrong, right? Like a lot of times. Using vocoder and stuff, like, what is your take on?
I mean, if you use the noisy phase, I mean, very very quick, you're going to realize that you get limited in terms of the performance you can get. I mean, actually using the noisy phase, even if you have perfect magnitude, by using the noisy phase, you can actually regenerate the other source. When you reconstruct in the waveform domain, the phase, the fact that the information about the other source is present in the phase can actually reconstruct the other source. I mean, once you reach a certain level, I think phase modeling is very important. That being said, it also depends on your application. If your application is ASR, for example, it probably doesn't matter that much because you're not going to use the phase. And in the end, you're going to do a feature extractor that is based on the magnitude, which is why it's maybe more important to focus on a loss function that involves the magnitude in that case. Actually, as a side note about phase, I had a paper maybe in 2009, I think, about trying to illustrate how much information you can have in the phase signal, and you can kind of you can play games and modify your magnitude spectrogram of just an isolated sound, like a speech signal, for example. You can modify that spectrum ever so slightly that by associating with it the right phase, you can reconstruct pretty much any signal you want. So you can tweak the phase in a way that all the basically what phase does, it takes the magnitude at a time frequency bin and points it in one direction, right? And then you can kind of use the phase to point all these time frequency bins in a certain direction, such that when you do overlap and add in the inverse short time Fourier transform, they all cancel out perfectly. That's actually very easy to do, right? To have them cancel out is trivial. But you can then cancel out, not quite, but such that they leave just a little bit of signal that such that at each time frequency bin, they leave a little bit of signal. And when you boost that signal, you just multiply it by 1,000 something, you can reconstruct like a rock music, for example. So you can basically, the only information about the rock music is in the phase that you associate. And in the overlap and add, everything cancels out and just leaves out the rock music, which is, I think, super surprising. So basically, you can play games. I mean, I'm not saying that this is useful or anything, but just to illustrate that there can be a lot of information in the phase that once you do the overlap and add can get uncovered. And you.
That is also the intuition of your network sequence, right? Like you want to do source separation first and then reverberate, not the other way around.
I'm not sure I see the connection. I have to think about that. I'm not sure I see the connection.
Is there a specific intuition behind the sequence, or?
Yeah, I mean, I think the sequence was, as I mentioned, like doing reverberation. You can do much better reverberation. Right. Well, I mean, I think the intuition about the first time we did this cascade was that because the speakers are at different locations, you really need the dereverberation to be on each speaker separately. You cannot apply the same dereverberation filter to both speakers because they are not in the same location. So, so they need different. Inherently, they need separate filters. So if you apply a dereverberation network to a mixture of speakers, unless they're in the same location, it's not. I mean, it's going to have to do different treatment for each of them, which sounds very hard. Okay.
So because you don't know, the input query can be anything, and it can have a long list of hierarchies that you can form. And
right.
These are generally based on our notion as to what the hierarchy should be.
Yeah. Yeah, that's a good question. So in this work, we just imposed a hierarchy. We had an ontology of instruments that was fixed. but yeah, discovering the hierarchy in natural sounds, I mean, that sounds super exciting. We're never able to figure out like a good way to do it. Like also, this, as you said, like depending on, there's so many different hierarchies that you could have, right? So which one you pick and which, I mean, depends on the problem. And but I think, yeah, like trying to discover the hierarchy is like something that I find very interesting.
I think let's thank Jonathan one more time.
Thank you.